Hi, you guys. Today I have with me problem 7.21 from Young and Freedman's University Physics textbook. Let's get started. A spring of negligible mass has force constant K is equal to 1600 newtons per meter. A, how far must the spring be compressed for 3.20 joules of potential energy to be stored in it? B, you place the spring vertically with one end on the floor. You then drop a 1.20 kilogram book onto it from a height of 0.800 meters from above the top of the spring. Find the maximum distance the spring will be compressed. Okay, so let's go ahead and just first jot down all of our knowns. So our knowns are, we have K, right? So we have our constant to 1600 newtons per meter. Then we have how far must the spring be compressed for 3.20 joules of potential energy. So the potential energy, oh, this is lowercase k, by the way. Sorry, I should rewrite that. And potential energy is 3.20 joules. Okay. And what else do we have? We have a book with a mass of 1.20 kilograms. And from a height, so we have a height of 0.800 above the top of the spring. Okay, cool. So let's actually go ahead and draw this. I know that usually I like to draw first, but just mixing things up today. So we have a spring first. So let's go ahead and draw this spring. And it seems to me that the way the spring is set up is that it's from like the bottom, like the floor, there's a spring, and then there's just some surface where we can like place things. Okay. And what's happening is that a book, so this is our book, let's say, is being dropped. And the height that it's being dropped is, so let's say like center of the book all the way to the top of this spring is 0.80 meters. Okay, so find the maximum distance the spring will be compressed. So yeah, what is, obviously like when we drop the book, what's going to happen is that the spring is going to be compressed, right, down to like some sort of distance, right? And we want to know what the maximum will be. So like, what's this distance going to be? So let's just say this is like X. This is the maximum distance that it's compressed, right? Makes sense? Okay, so now let's go back to A. So A is asking, how far must the spring be compressed for 3.20 joules of potential energy to be stored in it? Okay, so we want to know how far the spring must be compressed. So we want to know the distance. So let's just call the distance that the spring must be compressed. So let's call D the distance. Let's call D the distance, or like the distance that the spring is going to be compressed when the potential energy stored in the spring is 3.20 joules. Okay, perfect. So we're looking for this. So what is potential energy that's going to be stored in the spring? We know the formula for this is U is equal to half of kx squared. So I'm just keeping U here, even though I think it's capital K, but it says potential energy, and usually potential energy is U, but that's for gravitational potential energy. Maybe actually I can just go ahead and just right, this is capital K. I think that's a symbol for kinetic energy. Like, again, this just can be anything as long as you know what it is. Okay, so we are looking for, this is the maximum distance, right? Or how far the spring is going to be compressed. This is the distance of compression. This is the K constant. This is just a coefficient of half, and this is the potential energy stored. So if the potential energy stored is 3.20 is equal to a half, and then K is 1600 newtons per meter, and we are looking for what x squared is. Right? And I just realized at this point that I actually should have gone ahead and like isolated for x or isolated for Okay, so the reason why I just did or said is that we said this maximum distance is x, right? And I'm only using d here because I don't want to confuse you, because like this d and this x are not the same. They're going to be different values because the question is asking for two different distances. So for the sake of problem A, I'm just going to rewrite this formula as k is equal to a half of k d squared, right? But like x is just the distance. But yeah, this is what we're looking for. Again, it really doesn't matter like what letters you're using. There's usually just like a notation that you should be using, but you can put any letter of the alphabet here that you would like, right? If this is on an exam, your professor might not know what you're doing. So good rule of thumb is just to follow what your teacher or professor is doing, and then just use that notation in your, use those letters when you're solving problems. There we go. Okay. Now, next, we want to isolate for this x or this d here, I guess, right? So we want to isolate for d. Let's do that here. So 2k, capital K, divided by lowercase k is equal to d squared. You with me? That means that square root of this distance, right, is square root of 2 times the potential energy over the K constant is equal to the distance. Now remember that whenever we square root something, it's plus and minus, and this actually makes sense, right? Because when we have a spring, right? Oh, that was horrible. Let me redraw that. Well, when we have spring, right? And let's say this is like where the spring is at equilibrium, right? We know that, like, let's say we pushed it this way, the spring, it's going to oscillate here, right? So it's going to move this way, and then it's going to move out here, and then the spring's going to stretch. It's going to look like that, right? And this x, the reason why we have plus and minus here is because if this is equilibrium, right, it can move in the negative direction, and it can move in the positive direction, right? So that's why we have like plus and minus d or x or whatever you want to call it. Awesome. Okay, so now let's actually plug in our values. So our values just, it's going to be 3.2 times 2 over 1600 and square root that. And then that means that the x I'm getting is let me do that again. 1 second. I feel like oh, okay, I forgot to square root it. It's getting a different answer than I had before. So yeah, double check and let me know if this is also what you got on your calculator, but it should be right. I mean, it is right. I checked the back of the textbook, or I checked the solution manual as well. But yeah, okay, so we get 0.063 meters. So that is The distance, that's D. So that's how far the spring is going to be compressed for 3.20 joules of potential energy to be stored in it. Perfect. Okay. So now let's look at B. So B is asking you place the spring vertically with one end on the floor. You drop a 1.20 kilogram book onto it from a height of 0.800 meters above the top of the spring. Find the maximum distance the spring will be compressed. This is an interesting question, okay? So of course, this is a conservation of energy question. So we know that if this book is at some height, right? It's at some height right over here. That means that over here, it has gravitational potential energy. And then when it's completely compressed, all of that gravitational potential energy is converted to elastic potential energy. Okay, so that means that because of conservation of energy, at both of these points, the energy is going to be the same. So let's write down that in an equation. So at 1, it's going to be U, right? U is equal to mgh. And then elastic potential energy, which is capital K, is going to be half of kx squared, right? And here, okay, actually, I'll get to that in a second. So let's go ahead and first write down our equation. So this is what we're writing out, right? Because at this point right over here, all we have is gravitational potential energy. And then here, the only type of energy we have is elastic potential energy, right? And here, there's going to be a mixture of kinetic and gravitational potential. And then like right here, it's going to be a mixture of gravitational, potential, and kinetic, right? Also, I just realized that K is actually not the right notation, but again, it really doesn't matter because K is actually the kinetic energy one. I actually forget which one it is for you, but I'll figure it out next time and I'll have like the right notation for you. Or like the most common one that's used in the textbook, but like again, it doesn't matter. You can call these, you can put like, you can use any letters you want really, as long as it makes sense to you and as long as you're doing the math correctly. Okay. So at 1, we have mgh is equal to half of kx squared, right? Because this is state 1 and this is like at point 1 and at point 2, right? And we want to know the maximum distance that this is compressed. But remember, we don't want to mistaken this x distance with this x distance. Because truly, never mind, ignore what I said. Yes, this x is the exact same as this x, right? Now, the difference is that this h is from this point above. We are looking, if we set the equilibrium point of the spring as 0, right? This point, so that if we can set the 0 to be the equilibrium point of the spring. Okay. So that means h is equal to this 0.8 and this x, right? So mg is equal to 0.8 plus x is equal to half of kx squared. Okay, and we're looking for the maximum distance that the spring will be compressed. So we're looking for the value of x. Okay. And how we can do that is using quadratic equation. So let's go ahead and just write that out, right? So we have mg times 0.8 plus mgx is equal to half of kx squared, right? So I'm just going to go ahead and change the color so that we can see this all a little bit better. So if we want to write this down in the same, like in the quadratic format, like ax squared plus bx plus c, how we would do that is half of kx squared plus mgx, right? Or minus, sorry, minus. Minus mgx minus 0.8 mg, right, is equal to 0. So yeah, this is a quadratic because we have x squared, x, and then we just have a constant here, right? So now the next thing we want to do is we want to solve for this x. And how we do that is going to be by, yeah, we can use the quadratic equation, right? So I'm going to write that down actually right over here. I'm going to erase this part because we're already done with it. Continued. Okay. So what that equation would look like, and again, like, let me know if you get the same thing. I have double checked my work, but sometimes when I'm writing stuff out, I like forget a plus or minus. So usually the math is right. I just usually write, not usually, but sometimes I write out maybe one thing wrong. Like I'll miss a minus sign or something, right? Okay, so this is what we have. And then when we plug in all of our values, which I'm not going to do because for sure I'm going to mess up writing it and then you'll be confused. So this is going to be the answer for x, right? And so we get two answers. And I'm going to write down what I have here. And I'm going to double check on my calculator as well. But we have plus 11.76, right? M times G, plus minus 11.76 squared, plus 3105.6 over 1600. And that is equal to plus, let's see, that is equal to 0.116. And I'm just gonna like double check that on my calculator. My least favorite thing in the world is to plug things into, like plug the quadratic equation into my calculator, just because I feel like every single time I for sure mess up and have to do it like 4 times because I'll forget to like square root something or I'll divide the wrong thing. But okay, yeah. So the answer that I'm getting is 0.116 meters. So that is going to be the maximum compression, the maximum distance that the spring will be compressed. So that is the solution to 7.21. I hope that was helpful. Of course, if you have any questions, feel free to ask them in the comments or send me an email. And thank you so much for watching. Please don't